Howdy, guys. Jimmy Song here. Welcome to another episode of Off Chain. I'm doing a special episode, and this is something that, if it's popular enough, that I'll do on a more regular basis. And basically what I'm going to do today is go through BIP-340. If you're not familiar with BIP-340, this is the new number that was assigned to one of the three BIPs that are all part of what we're calling Taproot, or the next soft fork in Bitcoin. So as a part of that, I wanted to read through it and go through what it means, what it says, and basically just read it straight up, read it and tell you what it means. And hopefully that's useful to you. And if you find this valuable, please smash the like button and subscribe to my channel and let me know if it's useful to you, if it's something that you find valuable. If it is, I'll try to do more of these. If it's not, then, it's still kind of fun to do anyway. All right. So anyway, let's kind of get started. Here is BIP-340, and you can't find this in Bitcoin BIP's repository of GitHub. You actually have to go through the pull request, and this is in github.com, SIPA, BIPs, blob, BIP Taproot, BIP-340 Media Wiki. I think I put this in the show notes. But basically, this is the BIP-340 in SIPA. SIPA is Peter Woola. He's the one that actually has this pull request out. So this is where I am taking a look at it. It did get assigned numbers: BIP-340, 341, 342, 340 is Schnorr signatures for SecP 256K1. So without further ado, let's get going on examining what it says. All right, so the BIP number is 340. Title is Schnorr signatures for SecP 256K1. The three principals here for this particular BIP is Peter Woola, Jonas Nick, and Tim Ruffing. No comments yet. Comments URI. It's a draft status. It'll probably get on the standards track fairly quick. Yeah, it is standards track. BSD 2 clause created, I guess, a couple days ago. And there's a post history. Wow, I guess it's from July of 2018. So lots of stuff there. But let's get to the actual BIP and read through it. All right, abstract. This document proposes a standard for 64-byte Schnorr signatures over elliptic curve SecP 256K1. All right, so let's start with what you probably may not be familiar with, which is that currently we are using ECDSA signatures, and ECDSA signatures are roughly 71 bytes most of the time. They can be actually bigger, but they use something called the Dur encoding, which is kind of inefficient. So there are 7 bytes that are typically not very useful, or they don't really add anything. They're marker bytes and so on that are used. And for that reason, defining a standard for a Schnorr signature that's smaller, that can help is very important, because every transaction usually has at least one signature, oftentimes many if it's multi-sig and so on. And if a transaction is like 300 bytes, it might have like one signature. If it's like 500 bytes, it might have like 3 or 4. But each signature can be reduced by like 10% by using Schnorr signatures. So this will help in many ways to reduce the block usage and so on. This document is licensed under the 2-clause BSD license. This is different than the 3-clause. It's a very simple license. All right, motivation. Bitcoin has traditionally used ECDSA signatures over SecP 256K1 curve with SHA-256 hashes for authenticating transactions. These are standardized but have a number of downsides compared to Schnorr signatures over the same curve. I think he's going to basically describe what I just said to you. But yeah, provable security. Schnorr signatures are provably secure. In more detail, they are strongly unforgeable under chosen message attack, SUFCMA. In the random oracle model, assuming the hardness of the elliptic curve discrete logarithm problem, and in the generic group model, assuming variance of pre-image and second pre-image resistance of the used hash function. In contrast, the best known results for the provable security of ECDSA rely on stronger assumptions. Now, this is kind of getting in the weeds a little bit, but essentially, Schnorr signatures require less cryptographic assumptions to continue. If any of those assumptions kind of break, then the whole algorithm is broken, which basically it's saying from a security standpoint, Schnorr is just better. All right, non-malleability. The SUF-CMA security of Schnorr signatures implies that they are not malleable. On the other hand, ECDSA signatures are inherently malleable. A third party without access to the secret key can alter an existing valid signature for a given public key and message into another signature that is valid for the same key and message. This issue is discussed in BIP-62 and BIP-146. This is part of the malleability vector that was used supposedly for like a lot of the Mt. Gox stuff. But malleability is a major concern, especially because of Lightning, because you need a commitment transaction before that happens. And this was why SegWit was so important. And this hardens the malleability even more by having a different by reducing that malleability vector even further. Linearity. Schnorr signatures provide a simple and efficient method that enables collaborator parties to produce a signature that is valid for the sum of their public keys. This is the building block for higher level constructions that improve efficiency and privacy, such as multi-signatures and others. So in other words, what you can do with Schnorr signatures is aggregate signatures and aggregate pub keys. This is very, very useful because you don't need to show every pub key and you don't need to show every signature. You sum up the pub keys and you get a single public key, and you can sum up the signatures and get a single signature. That's very powerful because on the blockchain you only see one public key, one signature. You don't know if it comes from one key or many keys, and I'm sure he'll get into that later. For all these advantages, there are virtually no disadvantages apart from not being standardized. The thing that's kind of unsaid here was that Schnorr was under patent in the United States up until a few years ago. And this is assumed to be one of the reasons why Satoshi didn't use Schnorr signatures and instead used DSA, was because Schnorr signatures were under patent. This document seeks to change that. As we propose a new standard, a number of improvements not specific to Schnorr signatures can be made. Signature encoding. Instead of using dir encoding signatures, which are variable size up to 72 bytes, this is exactly what I told you before, we can use a simple fixed 64-byte format. So dir signatures are have a lot of scaffolding that you kind of have to put in. You have to tell people that what the next field's going to be, how long it is, and so on. This is the 6, 7, 8 byte tax that you have to pay every time. This reduces that by using a dir and instead of getting rid of the dir encoding and using something else. Public key encoding. Instead of using compressed 33-byte encodings of elliptic curve points, which are common in Bitcoin today, public keys in the proposal are encoded as 32 bytes. So currently, we're using compressed sec pub keys, so we're going to compress that even further to 32. This will be interesting as well. Batch verification. The specific formula of ECDSA signatures that is standardized cannot be verified more efficiently in batch compared to individually unless additional witness data is added. Changing the signature scheme offers an opportunity to address this. So there's a way to do batch verification that you can do with Schnorr that takes a lot more of the CPU usage down even further. With ECDSA, what you have to do is verify each signature individually. With Schnorr, you can use certain mathematical tricks to verify a batch of them at the same time, and that's a really, really useful thing. Completely specified. To be safe for usage in consensus systems, the verification algorithm must be completely specified at the byte level. This guarantees that nobody can construct a signature that is valid to some verifiers, but not all. This is traditionally not a requirement for digital signature schemes, and the lack of exact specification for the dir parsing of ECDSA signatures has caused problems for Bitcoin in the past, and needing BIP-66 to address it. In this document, we aim to meet this property by design. For batch verification, which is inherently non-deterministic, as the verifier can choose their batches, this property implies that the outcome of the verification may only differ from individual verifications with negligible probability, even to an attacker who intentionally tries to make batch and non-batch verifications differ. So in other words, part of the problem with ECDSA and really signature schemes in general in the context of consensus systems is that there really isn't a a byte for byte specification for verification. And that's what this document is trying to produce is that specification, so it's more appropriate for the use case that we're using it for, which is Bitcoin. And kind of getting rid of ECDSA signatures and going to Schnorr signatures allows us to have this additional thing. By reusing the same curve and hash function as Bitcoin uses for ECDSA, we are able to retain existing mechanisms for choosing secret and public keys, and we avoid introducing new assumptions about the security of elliptic curves and hash functions. Absolutely true. So we're going to keep the BIP-256K1 curve. We could move to another curve. A popular one is something like EDDSA, ED25519, that's using EDDSA that like Monero uses and some others use, but that's not even an elliptic curve. It's I forget what the curve is called, but it's a different type of curve and it uses a different formula. But by not having to, by sort of keeping the security properties as close to the current signature scheme as possible, we don't have to add any new assumptions or be exposed to anything more than we currently are. Description. We first build up the algebraic formulation of the signature scheme by going through the design choices. Afterward, we specify the exact encodings and operations. Great. Design. Signature, Schnorr signature variant. Elliptic curve Schnorr signatures for message M and public key P generally involve a point R, integers E and S picked by the signer, and the base point G, which satisfy equals hash of R concatenated with M, and S times G equals R plus E times P. Two formulations exist depending on whether the signer reveals E or R. Okay, so a lot of this might kind of sound like Readthrough unless you've taken my class or read my book. By the way, if you are interested in doing that, I encourage you to take my class in Las Vegas. You'll understand this a lot better after you learn just what elliptic curve cryptography is, because you need to know that in order to know elliptic curve Schnorr signatures. Signatures are pairs ES that satisfy E equals hash of S times G minus E times P concatenated with M. This variant avoids minor complexity introduced by the encoding of the point R in the signature. See paragraphs encoding R and the public point P and implicit Y coordinates further below in the subsection. Moreover, revealing E instead of R allows for potentially shorter signatures, whereas an encoding of R inherently needs 32 bytes. The hash E can be tuned to be shorter than 32 bytes, and a short hash of only 16 bytes suffices to provide SUF-CMA security at the target security level of 128 bits. This is, again, kind of getting into the weeds, but basically, ECDSA encodes capital R, which is a public point in the SecP-256K1 curve. Encoding and not R necessarily. It actually takes the X coordinate of the point R and then derives Y off of it. But what this is saying is instead of that, we can send E, which is the hash of this sum, and use that. And you can actually even shorten shorten E considerably to 16 bytes and still get 128 bits level security. However, a major drawback of this optimization is that finding collisions in a short hash function is easy. This complicates the implementation of secure signing protocols in scenarios in which a group of mutually distrusting signers work together to produce a single joint signature. See applications below. In these scenarios, which are not captured by the SUF-CMA model due to its assumption of a single honest signer, a promising attack strategy for malicious cosigners is to find the collision in the hash function in order to obtain a valid signature on a message that an honest cosigner did not intend to sign. All right, so I should probably put in a pull request there because that's a grammatical error. Did not intend to sign. But yeah, basically, what this is saying is you can use a shorter hash and have the target security level. But then you're making it so that hash collisions become more valuable, and you don't really want that, especially because that can cause problems and cause people to sign things that they didn't intend and so on. Signatures are pairs RS that satisfy S times G equals R plus hash of R concatenated with M times P. This supports batch verification as there are no elliptic curve operations inside the hashes. Batch verification enables significant speed up. So one of the problems with having an elliptic curve operation inside the hash function, you can see that there's no elliptic curve operation here. It's a concatenation of R and M. There's no multiplication of R or anything like that. I believe there is one in ECDSA. That means that you can have batch verification, and that means that you can verify a whole bunch of transactions at once instead of checking each signature individually. So the speed up can be fairly significant, and you can you're getting some significant speed up over a single verification. This graph shows the ratio between the time it takes to verify n signatures individually and to batch verify n signatures. The ratio goes up logarithmically with the number of signatures, or in other words, the total time to verify n signatures grows with O of n over log n. Since we would like to avoid the fragility that comes with the short hashes, the E variant does not provide significant advantages. We choose the R option, which supports batch verification. So instead of using E, which may allow for shorter hashes, they're choosing the R option, which supports batch verification, which is a big win. And from a design perspective, that is the correct choice to make here. Key prefixing. Using the verification rule above directly makes Schnorr signatures vulnerable to related key attacks in which a third party can convert a signature, RS for a public key P, into a signature R, S plus A times hash of R concatenated with M for public key P plus AG and the same message M for any given additive tweak A to the signing key. This would render signatures insecure when keys are generated using BIP-32's unhardened derivation and other methods that rely on additive tweaks to existing keys such as taproot. So basically, this means that you have to add something else because you can't just use the verification rule as sort of stated in the first couple of things, because there is a way to render the signature insecure. To protect against these attacks, we choose a key prefixed Schnorr signatures. Changing the equation, S times G equals R plus hash of R concatenated with P concatenated with M times P. So you have to put P into the hash function as a way to make it so that you can't do the chosen prefix attack. It can be shown that key prefixing protects against related key attacks with additive tweaks. In general, key prefixing increases robustness in multi-user settings. For example, it seems to be a requirement for proving the music multi-signature scheme secure. See applications below. So basically, to protect against the related key attack, which is known, this is a way to make it using the key prefix Schnorr signatures. We have protection against that. We know that key prefixing is not strictly necessarily for transaction signatures as used in Bitcoin currently because signed transactions indirectly commit to the public key already. M contains a commitment to PK, to the public key. However, this indirect commitment should not be relied upon because it may change with proposals such as SigHash no input BIP-118 and would render the signature scheme unsuitable for other purposes than signing transactions. For example, signing ordinary messages. And this is absolutely true. You want signatures to be a little more general than for signature transactions only, as when people prove that they have funds or something like that by signing a particular message. Encoding R and the public point P, there exists several possibilities for encoding elliptic curve points using the full X and Y coordinates of P and R, resulting in a 64-byte public key and a 96-byte signature. So that's generally not a good idea. That's more or less the uncompressed pub key. Use encoding the full x coordinate and 1 bit of the y coordinate to determine one of the 2 possible y coordinates. This would result in a 33-byte public keys and 65-byte signatures, and this is exactly what compressed secpub keys are. It's just using the x coordinate and the parity of the y. Encoding only the x coordinate, resulting in 32-byte public keys and 64-byte signatures. So if you just encode the x coordinate, you can do, I think, 4 operations and figure out what the y coordinate is and see if any of them are valid with the particular signature. Using the first option would be slightly more efficient for verification, around 10%, but we prioritize compactness and therefore choose option 3. Implicit y coordinates. In order to support efficient verification and batch verification, the y coordinate of P and of R cannot be ambiguous. Every valid x coordinate has 2 possible y coordinates, and this is because the elliptic curve is symmetric over the x-axis. We have a choice between several options for symmetry breaking: implicitly choosing the y coordinate that is in the lower half, implicitly choosing the y coordinate that is even, implicitly choosing the y coordinate that is a quadratic residue, has a square root modulo the field size, or is a square for short. In the case of R, the third option is slower at signing time, but is faster, a bit faster to verify, as it is possible to directly compute whether the y-coordinate is a square when the points are represented in Jacobian coordinates, a common optimization to avoid modular inverses for elliptic curve operations. Now, I have worked with Jacobian coordinates before. It's a way, instead of just x and y, there's like a z that's computed for x and y that make a lot of the computation a lot simpler. And yeah, that's like seriously getting into the weeds. But essentially, Jacobian coordinates let you save CPU time when doing computations for elliptic curve operations. The other 2 options require a possibly expensive conversion to affine coordinates first. This would even be the case if the sign or oddness were explicitly coded, option 2 in the list above. Therefore, we choose option 3. So the other coordinate system is Jacobian is the XYZ, affine is XY. You can convert between both, but the affine coordinate conversion is rather expensive. So in order to decrease CPU time, the design consideration, being the verification being the main design consideration, option 3 is chosen. So very good design choice, totally makes sense. You can see the reasoning for the design choices that are being made here, which is to reduce whatever goes into the blockchain and make it as easy on the verifiers as possible, and put the burden on the signers to produce the signatures. For P, the speed of signing and verification does not significantly differ between any of the 3 options, because affine coordinates of the point have to be computed anyway. For consistency, if you're going to transmit P, you have to compute affine. That's basically what it is. For consistency reasons, we choose the same option as for R. The signing algorithm ensures that the signature is valid under the correct public key by negating the secret key if necessary. Right. Okay. So you can negate the secret key. So, interesting. So it could be P times G or N minus P times G. Okay, great. All right. Implicit y coordinates are not a reduction in security when expressed as the number of elliptic curve operations as attacker is expected to perform to compute the secret key. An attacker can normalize any given public key to a point whose y coordinate is a square by negating the point if necessary. This is just a subtraction of field elements and not an elliptic curve operation. Because we know n, which is the order of the group that's being used. We can just do n minus the secret if things don't work out, basically. Tagged hashes. Cryptographic hash functions are used for multiple purposes in the specification below and in Bitcoin and in general. To make sure hashes used in one context can't be reinterpreted in another one, hash functions can be tweaked with a context-dependent tag name in such a way that collisions across contexts can be assumed to be infeasible. Such collisions obviously cannot be ruled out completely, but only for schemes using tagging with a unique name. As for other schemes, collisions are at least less likely with tagging than without. For example, without tagged hashing, a BIP-340 signature could also be valid for a signature scheme where the only difference is that the arguments to the hash function are reordered. Worse, if the BIP-340 nonce derivation function was copied or independently created, then the nonce would be accidentally reused in the other scheme, leaking the private key. Yeah, so you don't want nonce reuse. Nonce stands for number used only once, and you don't want to do that, because if you show the nonce, if you reuse the nonce or sign with the two different nonces the same thing, you essentially leak the private key, which you do not want to do. That's very, very bad. And this is one of the major security things that you have to be concerned with as a wallet developer. This proposal suggests to include the tag by prefixing the hash data with SHA-256 of tag, or SHA-256, so concatenated. Because this is a 64-byte long context-specific constant, and the SHA-256 block size is also 64 bytes, optimized implementations are possible, identical to SHA-256 itself, but with a modified initial state. Using SHA-256 of the tag name itself is a reasonably simple and efficient for implementations that don't choose to use the optimization. All right, so it's simple and you can still do it. Final scheme. As a result, our final scheme ends up using public key pk, which is the x-coordinate of a point P of the curve whose y-coordinate is a square, and signatures rs, where r is the x-coordinate of a point R whose y-coordinate is a square. The signature satisfied s times g equals r plus tagged hash r pk m times p. All right, so again, that's getting into the weeds a little bit with the elliptic curve cryptography. And if you are curious, I encourage you to take my class or read my book, and you can understand a lot more of why that works. Specification. The following conventions are used with constants as specified for SEC P256K1. Lowercase variables represent integers or byte arrays. The constant P refers to the field size, and that is the field size used for the elliptic curve. Constant n refers to the curve order. This is, again, it's in the book if you want to know more about it. It's basically how many times you have to add g before it comes back to 0. Uppercase variables refer to points on the curve with equation y squared equals x cubed plus 7. That is the equation for SEC P256K1 over the integers modulo p. Is finite p returns whether or not p is the point at infinity. Great. So it can be the point at infinity, which is essentially 0 in the group math context. X of p and y of p are integers in the range of 0 to p minus 1 and refer to the x and y coordinates of a point p. So every point has an x and y coordinate, and this is what you would also call the affine coordinate system. The constant g refers to the base point for which x of g is this and y of g is this. So g is the generator point. You could basically choose any generator point. Andy Polstra has told me exactly how they're generated. I forget exactly why, but there is a nothing up my sleeve way of generating the generator point. Addition of points refer to the usual elliptic curve group operation. Yep. That's what you would call point addition. Multiplication of an integer and a point refers to repeated applications of the group operations. This is what you would call scalar multiplication from the book. Functions and operations. The double pipe symbol refers to byte array concatenation. The function x of I to j, where x is a byte array, returns j minus I byte array with a copy of the ith byte inclusive to the jth byte exclusive of x. So it's every byte in x from I to 1 less than j, basically. The function bytes x, where x is an integer, returns a 32-byte encoding of x, most significant byte first. So this is a big endian interpretation of x as a number. The function bytes p, where p is a point, returns bytes x of p. So you take the x coordinate and then you get the big endian representation of that x coordinate. The function int x, where x is a 32-byte array, returns a 256-bit unsigned integer whose most significant byte first encoding is x. So it's you turn it back. So it's the inverse of the bytes x function. The function is square x, where x is an integer, returns whether or not x is a quadratic residue modulo p. Since p is prime, it is equivalent to the Lagrange symbol being equal to 1. So it's a way to figure out if x is a square, and only certain numbers are squares in this. The function has square y p, where p is a point, is defined as not is infinite p and is square y of p. Has square is it can't be an infinite. It can't be the point at infinity, and it is a square. So the point at infinity is a square of the point at infinity. So that's kind of trivially true. So we're excluding that, and has square y excludes the point at infinity essentially, and is a square. The function lift xx, where x is an integer in the range of 0 to p minus 1, returns the point p for which x of p equals x, and has square y p, or fails if no such point exists. So x of p equals x, and has square y of p. Okay, or fails if no such point exists. The function lift xx is equivalent to the function following pseudocode. Let c equals x cubed plus 7 mod p. Okay, let y equal to c to the p plus 1 divided by 4. That's essentially the square root formula. Fail if c not equal to y squared. Return the unique point p such that x of p equals x and y of p equals y, or fail if no such point exists. So basically, x of p is the x coordinate of p, and y of p is the y coordinate of p. You're looking for the point where the y is where this thing is a square, and this is necessary because of the design choices made earlier. The function point x, where x is a 32-byte array, returns the point p equals lift x int x. Okay. So you get the actual point that was used in the signature. That's essentially what that gets you. The function hashtag x, where tag is a UTF-8 encoded tag name, and x is a byte array, and returns a 32-byte hash of SHA-256 of the SHA-256 of the tag, concatenated with the SHA-256 of the tag, concatenated with x. All right, public key generation, the secret K, SK, a 32-byte array generated uniformly at random. Okay, yeah, and that is your secret. This is the thing that you are trying to protect whenever you are, using a wallet or whatever. Public key generation, input, the secret key, the algorithm public key sk, as defined as d equals int of sk, fail if d equals 0 or d is greater than or equal to n, return bytes of d times g. Yeah, and this is a typical way of generating a public key. You multiply it by the generator point. Note that we use a very different public key format, 32 bytes, than the ones used by existing systems, which typically use elliptic curve points as public keys, or 33-byte or 65-byte encodings of them. A side effect is that public key sk equals public key of bytes of n minus int sk. So every public key has two corresponding secret keys. Oh, interesting. Yeah, that is correct. So two different secret keys can generate the same pub key, your secret key and the negative of your secret key. As an alternative to generating keys randomly, it is also possible and safe to repurpose existing key generation algorithms for ECDSA in a compatible way. The secret keys constructed by such an algorithm can be used as SK directly. The public keys constructed by such an algorithm, assuming they use 33-byte compressed encoding, need to be converted by dropping the first byte. Specifically, BIP-32 and schemes built on top of it remain usable. So basically, BIP-32 defines HT wallets, which is more or less what every wallet uses. But instead of using the 33-byte compressed sec pub key, what you're going to need to do for the purposes of Schnorr signatures is to cut off that first byte and use the last 32. Because the first byte only tells you the parity, but instead of using the parity, what you're going to do is figure out which one's a square and use that. All right. Default signing input, the message key SK, a 32-byte array, the message M, a 32-byte array. The algorithm of sign SKM is defined as let D prime equal to integer SK, right? Interpret that as a big endian integer. Fail if D prime equals 0 or D prime greater than or equal to N. That just doesn't happen. Let P equal to D prime times G. Yep, that's a public point for our secret key. D equals D prime if it has square Y P. Otherwise, let D equal to N minus D. So if it's a square, then great. Otherwise, flip it and go with go with that. Go with the flipped one. So whatever your private key is, you can always generate the number, the actual secret key that you're going to use, or the multiple that you're going to use. Let rand equal BIP hash BIP Schnorr derivative bytes D concatenated with M. Okay, let K prime equal to int rand mod N. Fail if K prime equals 0. Let R equals K prime times G. Okay, so yeah, I mean it's not gonna fail there. Let K prime equal to integer of rand. Okay, so you want a mod by N after interpreting it as a big endian integer, and this is the key here, and the reason why Schnorr signatures are so elegant is that you can just use a hash, and this is the BIP Schnorr derived hash, and it's essentially taking the bytes of D, which is the inverse function for int of sk, and concatenating it with the message, and that's our K prime. Let R equal to K prime times G. So it looks like this is a deterministic K generation, which is great because you want that instead of choosing a K at random. K equal, you make sure that K prime has a square, otherwise n minus that. Let E equal to integer, mod N, okay. And return the signature of the bytes R, and bytes K plus ED mod N, and that's our S here, K plus ED mod N. Okay, great. So looks like deterministic K is sort of baked in there, which is great. Which is great for security because you don't have to rely on a random number generator in order to create a signature, which many wallets have failed in, and this caused funds to be stolen and so on. Alternative signing. It should be noted that various alternative signing algorithms can be used to produce equally valid signatures. The algorithm in the previous section is deterministic, i.e. it will always produce the same signature for a given message and secret key. This message does not need a random number generator at signing time and is thus trivially robust against failures of random number generators. Alternatively, the 32-byte rand value may be generated in other ways, producing a different but still valid signature. In other words, this is not a unique signature scheme. No matter which method is used to generate the rand value, the value must be a fresh, uniform, random 32-byte string, which is not even partially predictable for the attacker. So this is very important that you make it so that the K generation is very random. The particular algorithm here, the default one, it uses a deterministic K, which is great, especially for unit testing and so on. What this is saying is that you don't need to use that particular random or K generation algorithm. You can use another deterministic one, or if you really want a random number generator. Synthetic nonces. For instance, when an RNG is available, 32 bytes of RNG output can be appended to the input of the hash BIP Schnorr derivative. This will change the corresponding line in the signature algorithm to rand. This giant ugly thing is a call to the RNG, and that's a way to add entropy to your signature. Adding RNG output may improve protection against fault injection attacks and side channel attacks. That is also true. Side channels are within a device or something like that, and being able to listen in for certain things. And it is safe to add the output of a low entropy RNG. If you're XORing it, then you're not gonna you're only adding security. You're never subtracting. Nonce exfiltration protection. It is possible to strengthen the nonce generation algorithm using a second device. In this case, the second device contributes randomness which the actual signer provably incorporates into its nonce. This prevents certain attacks where the signer device is compromised and intentionally tries to leak the secret key through its non-selection. Ooh, yeah, that's a really good one, because exfiltration protection is particularly an attack vector for hardware wallets and so on. If the firmware gets leaked or something, but you don't have access to the secure element, the nonce being chosen can give information, and enough of those can leak your private key. Multi-signatures. This signature scheme is compatible with various types of multi-signature and threshold schemes such as MuSig, where a single public key requires the holders of multiple secret keys to participate in signing. See applications below. It is important to note that multi-signature signing schemes in general are insecure with the random generation from the default signing algorithm above or any other deterministic method. So MuSig is one of the big ones, and you can aggregate pub keys, you can aggregate signatures. One of the things that it's pointing out is that don't use the deterministic signing algorithm above for MuSig. You need to use something else, and in fact, you need to commit to certain things beforehand. Verification, the public key, message, and signature, 32, 32, 64 bytes respectively. The algorithm verify PK msig is defined as P is the point of the public key, and you need to interpret it as a public key. And then R is the first 32 bytes interpreted as a big endian integer, and it's basically the x coordinate of the resulting point. S is the last 32 bytes, and that is going to be used as a before the generator point, so it needs to be less than n. E is the hash of this thing, and R is this thing, and if and R has to have a square because we chose it that way, and x of R is not and the x coordinate of the resulting point has to equal R, which was given at the beginning. And a lot of digital signature algorithms are like that. You start with a number and you end with the same number. It's sort of like closing the loop. For every valid secret key SKM message M, verify pub key SKM sign SKM will succeed. Note that the correctness of verification relies on the fact that point PK always returns a point with a square y coordinate. A hypothetical verification algorithm that treats points as public keys and takes the point P directly as input would fail anytime a point with non-square y is used. While it is possible to correct for this by negating points with non-square y coordinate before further processing, this would result in a scheme where every message pair is valid for two public keys, a type of malleability that exists for ECDSA as well, but we don't wish to retain. We avoid these problems by treating just the x coordinate as a public key. So in other words, like there is a malleability in ECDSA using compressed pub keys that allow a particular message to be valid for multiple ones. So usually the negation of something. So this is taking away that malleability vector as a design choice. Very good idea. Batch verification. All right, so this is something that I'm not sure I fully understand yet, but it is very important because it does make verification speed up so much faster and so on. The input is the number of U of signatures, the public keys 1 through U 32 byte arrays, the messages U 32 byte arrays, the signatures U 64 byte arrays. The algorithm batch verify is defined as generate U-1 random integers and range 1 through n-1. They are generated deterministically using a CSP RNG seeded by a cryptographic hash of all inputs of the algorithm. So there's a function that where you take all the cryptographic hash of the algorithms, and you have a new function that will generate a bunch of integers. Seed equals, it's some concatenation of all of them. Safe choice is to instantiate seed hash with SHA-256 and use cha-cha-20 with the key seed as a CSPRNG to generate 256-bit integers, skipping integers not in the range 1, 2, and -1. Great. Okay, for I equals 1 to U, all right, so it's a for loop here. For PI equals point of PKI fail if point PKI fails, okay. Fail if R, yep, this is a big endian, little endian, big endian, first 32 bytes, big endian, last 32 bytes. And this is E, and this is R. So, oh, you do a running total. Yeah, that's right. Yeah, you do a running total of um, all of the sums and these random integers, and you apply the random integers to all of the R's. And if they're equal, then all of them are equal because of the assumptions that are made and going into this. So if all of these sums are correct, then every one of them is correct, and you can't create another one that without breaking discrete log in order to make it work. So yeah, that's exactly how batch verification should work. Well done. If all individual signatures are valid, verify would return success for them. Batch verify will always return success. If at least one signature is invalid, batch verify will return success with at most a negligible probability, and that's an insanely negligible probability, by the way, like on the order of like 1 out of 2 to the 256 times. So that way, yeah, that does speed up verification significantly, because you just keep a running total and you mod by n and so on. So this could be very, very efficient. Optimizations. Many techniques are known for optimizing elliptic curve implementations. Several of them apply here, but are out of the scope of this document. 2 are listed below, however, as they are relevant to the design decision. Squareness testing. The function is_x is defined as above, but can be computed more efficiently using an extended GCD algorithm. GCD is the greatest common denominator, and I think there's I forget who made that algorithm, but it makes it a lot faster. Jacobian coordinates. Elliptic curve operations can be implemented more efficiently using the Jacobian coordinates. Elliptic curve operations implemented in this way avoid many intermediate modular inverses, which are computationally expensive. And the scheme proposed in the document is in fact designed to not need any inversions at all for verification. When operating on a point R with Jacobian coordinates, which is not the point at infinity for which xp is defined as x divided by z squared and yp is defined as y divided by z cubed, has square yp can be implemented as is square yz mod p. X of p can be implemented as 0 less than or equal to r less than p, and z not equal to z squared r mod p. All right, so all that is to say, basically division in elliptic curve cryptography ends up being enormously expensive. This is what takes up a lot of your CPU time when you're doing signature and verification and so on. So by using Jacobian coordinates, you can avoid a lot of the inversions, or essentially divisions. And division is essentially inversion, right? Like if you have R, division is doing 1 over R. That's what an inversion is. So this makes for a much better optimization, or it can be implemented. It's a design decision to make it easy for nodes to be able to verify these things. All right, so there are a bunch of applications. All right, I guess it's not too long, so I'll read those too. There are several interesting applications behind simple signatures with recent academic papers. While recent academic papers claim that they are also possible with ECDSA, consensus support for external signature verification would significantly simplify the constructions, multi-signatures and threshold signatures. By means of an interactive scheme such as MuSig, participants can aggregate their public keys into a single public key, which they can jointly sign for. This allows n of n multi-signatures, which from a verifier's perspective are no different than ordinary signatures, giving improved privacy and efficiency versus check multisig or other means. So in other words, you can do multisig, or as long as it's like 3 of 3, 4 of 4, or whatever, using MuSig, that'll work. Moreover, Schnorr signatures are compatible with distributed keys generation, which enables interactive threshold signature schemes. For example, the schemes described by Stinson and Strobel, or Gararo, Jarecki, and I can't pronounce that, sorry. These protocols make it possible to realize k of n threshold signatures, which ensure that any subset of size k on the set of n signers can sign. But No subset of size less than k can produce a valid Schnorr signature. However, the practicality of the existing schemes is limited. Most schemes in the literature have been proven secure only for a case where k-1 is less than n over 2, are not secure when used concurrently in multiple sessions, or require a reliable broadcast mechanism to be secure. Further research is necessary to improve the situation. So there is a K of N music, Schnorr multi-sig scheme. They're just not ready yet. So that's something to think about with threshold signatures. Adapter signatures can be produced by a signer by offsetting his public nonce with a known point t equals t times g, but not offsetting his secret nonce. Correct signature or partial signature, as individual signers' contributions to a multi-sig are called, on the same message with the same nonce will then equal to the adapter signature offset by t, meaning that learning t is equivalent to learning the correct signature. This can be used to enable atomic swaps or even generate payment channels in which the atomicity of joint transactions is ensured using the signatures themselves rather than Bitcoin script support. The resulting transactions will appear to verifiers to be no different than ordinary single signer transactions, except perhaps for the inclusion of lock time refund logic. So adapter signatures basically allow you to do multi-sig and basically reveal T. Right now, the way channels are opened and closed and so on require you to show the hash of something, and then you show the pre-image when you're updating and so on. You could do that sort of at the signature level by holding back this T, which is added to everything else. Adapter signatures, beyond the efficiency and privacy benefits of encoding script semantics into constant size signatures, have additional benefits over traditional hash-based payment channels. Specifically, the secret values T may be reblinded between hops, allowing long chains of transactions to be made atomic, while even the participants cannot identify which transactions are part of the chain. Also, because the secret values are chosen at signing time rather than key generation time, existing outputs may be repurposed for different applications without recourse to the blockchain even multiple times. So it does allow a lot more flexibility for something like the Lightning Network, in other words. Blind signatures. Blind signature protocol is an interactive protocol that enables a signer to sign a message at the behest of another party without learning any information about the signed message or the signature. Schnorr signatures emit a very simple blind signature scheme, which is, however, insecure because it's vulnerable to Wagner's attack. A known mitigation is to let the signer abort a signing session with a certain probability, and the resulting scheme can be proven secure under non-standard cryptographic assumptions. Blind Schnorr signatures could, for example, be used in partially blind atomic swaps, a construction to enable transferring of coins mediated by an untrusted escrow agent without connecting the transactors in the public blockchain transaction graph. So it's not something that I know very much about, but it sounds like a way to do some sort of swap without knowing very much about each other and with very low trust. Test vectors and reference code. For development and testing purposes, we provide a collection of test vectors in CSV format and a naive, highly inefficient, and constant time pure Python 3.7 reference implementation of the signing and verification algorithm. The reference implementation is for demonstrative purposes only and not to be used in production environments. So here is the reference.py. Yeah, so all of the functions are essentially put in here. I should probably incorporate it into my library at some point. But yeah, it's very good. If there is something, if you're interested in me taking a look at this and or explaining it or something like that, maybe I can do that as well. Anyway, it's really cool stuff, and it looks like we had a bunch of viewers. Thank you guys for watching. It was my first full read through of this. I've seen bits and pieces, so it was good for me as well to read through it. Hope that helped you. I don't know how many of you honestly got something out of it. Maybe a bunch of you did. Maybe a bunch of you didn't. I did see a bunch of people drop out, so obviously it's not for everybody. But hopefully that helped you. Fiat delenda est. This song is done.